in the atomic sensor, we are talking about that what are the excellent quantum sensors, and why it is excellent, because it is having the 4 quality. Number 1 is identical, number 2 is isolation, number 3 is interfaceable, number 4 is intangible. So in this continuation, we are just discussing the third point, which is interfaceable. So the ability to remote manipulate and interrogate atomic quantum state using the light is the key enabling feature of the most atomic sensors. So that will make it a more efficient sensor and more effective. So the effective area of an atom interacting with a resonant photon is of order of lambda square, as the light and the atom will be in the resonance whenever they are interacting. So what area, that is the efficient area of an atom interacting with a resonant photon, that is the order of lambda square, which allow atomic states to be manipulated and detected by the light with exquisite sensitivity. So technologies such as compact tunable diode lasers, electro-optic modulators and ultra sensitive detectors provide an array of the powerful tool that allow practical atom detection and the manipulation at a near quantum limits in that particular area, that is the lambda square. Fourth is intangible. So it is in the most cases, atomic interaction can be realistically and quantitatively understood directly from the first principle, that is a Hamiltonian governing atoms, and their interaction with the electromagnetic fields are extremely well characterized, and even many important decoherence mechanisms have been well studied, allowing their consequences to be predicted with a high degree of confidence. So atomic sensor are basically of the various types. So atomic sensor type with the naive order of the magnitude established of the QPN of the centimeter scale, and vapor packaging, so exceeding small fundamental limit, represent the potential for highly measure the sensitivity. In practice, we can find out the technical noise that may be internal or the environmental is almost always order of the magnitude greater than these values. So here we are having the various properties of the atomic sensors, in which we will finding out the frequency, B field, E field, acceleration and the rotation. So these are the various, on the basis of that we can measure the various parameters. So is this table summarizing the various physical properties, their measurement methods, their sensitivity, their quantum projection noise, that is QPN values, so that we can protect from the noise which is likely in the context of the precision measurement using the atomic system. So these are the various parameters we can measure in the atomic sensors. Now the table compares with the precision of measuring the properties like frequency, like B field, magnetic field, like electric field, like acceleration, like rotation. So hyperfine splitting spectroscopy offers the high frequency precision. So whenever we require the high frequency precision, we use the hyperfine splitting. Rydberg-Stark effect is also used for detection of the electric field with the QPN. So that quantum projection noise also can be measured by the Rydberg-Stark effect. So now next point we come in the mind, that how we prepare for the quantum state. So next is the quantum state preparation. The specific varieties of quantum state preparation to reduce both the electronic and momentum degree of the freedom relevant to the atoms are too many to be usefully summarized. Instead, the several types, just we have the some points which are used for the preparation of the quantum state. First is the optical pumping. We know that whenever we are getting the sensing, so what are the parameters we are using with the quantum pumping? First is which is used of the light scattering, so to transfer the order from the light to the internal state of the atoms. First, the quantum, in the quantum state, first whenever we talk about the atomic quantum atomic sensors, in which first state we are having the optical pumping. That optical pumping is used of the light scattering to transfer order from light to the internal state of the atoms. There must be interaction with the light and the atom. So, given the various parameters, it follows that the varieties of optical pumping configurations are essentially limitless. So, what type of optical pumping we are using depend upon the atomic cloud. So, the cold atoms where the light scattering can be easily made to demonstrate over other forms of the decoherence, where we are having the collision, we are having the magnetic field fluctuations, etc. The atom will tend to accumulate in the dark state that minimize the light scattering rate. So, in optical pumping, in the cloud of cold atoms, where the light scatters can easily made to dominate over the other form of the decoherence. So, the atom will tend to accumulate in the dark states, and that minimize the light scattering rate. But in the hot atoms, optical pumping is not as fast due to Doppler or the collisional broadening of the excited state. Means we are having the fast movement of the light in the cold atmosphere, in the cold atoms, but in the hot, optical pumping is not as fast due to the Doppler or the collision broadening of the excited state. So, usually result in the balance between the light induced ordering and the collisional decoherence. So, next is the velocity selection. So, in case of the thermal equilibrium naturally produces nearly perfect electronic state, population imbalance such that electronic state preparation per se may be unnecessary. So, this is true in the system involving the excited electronic state such as the 2-photon optical clock and the Rydberg atom RF receiver. So, these both use the excited electronic state. Instead, a range of the velocity classes is selected using the direction of the light. So, in the Doppler effect that evoke the resonant condition within a subset of the momentum distribution of the atom. This is particularly in the Rydberg. Whenever we talk about the Rydberg, then we discuss about all these conditions. So, we are having the various systems which involve the excited electronic state. So, in the multi-photon processes, up to now we have discussed the 2-photon processes, but in the multi-photon processes, even if the net wave vector is k is equal to k1, k2 is small, so that the multi-photon resonance condition is effectively Doppler free. Because we are talking about the whenever we are just talking about the fast movement, so there must be the, in case of the multiple photon resonance condition which is effectively Doppler free. So, the process may yet be the velocity is selective if the intermediate state Doppler shift, that is the k1 plus k2 up to the nu, which are the comparable to the intermediate state line width. Another parameter is the laser cooling. So, laser cooling can be considered a generalization of the optical pumping to the external or the motional degree of the freedom of the atoms, as entropy is removed from the atoms by the light scattering of the spontaneous emission. So, laser cooling is the in the laser cooling there are a large number of different schemes of the laser cooling that are most effective, of which utilizing an interplay between the coherent and the incoherent state dependent forces. So, we are talking about the Stark effect and the scattering in case of the laser cooling. So, a typical laser cooling sequences involve the collectively room temperature atoms into a magneto-optical trap that must be 100 millisecond, which is a longer time. So, magnetic field gradient of the mode is switched off, the atoms are cooled in the optical molasses for the 10 millisecond. So, if we require, then we require the 10 micro, then we are required that we are having just further cooling at the temperature which is a 10 micro Kelvin, that the atoms can then be further cooled to the temperature below the recoil limit using the more complex technique such as Raman sideband cooling. And another example, that will be loaded into an optical lattice and dipole trap, then manipulated for purposes of the measurement. So, whenever we change the temperature or whenever we go to the cooling system at the below temperature, so we are using the different methods for the measurement. So, laser cooling can also be used as a starting point for the production of high phase space density clouds using evaporative cooling from conservative laser or the magnetic traps. So, in another fourth point, which is the coherent population trapping, means whenever we talk about the atomic vapor and we are talking about as using as a sensor. So, in this the two main point, one is the cooling, second is the trapping are required. So, coherent population trapping, a specialized form of the optical pumping, coherent population trapping, which are known as the electromagnetically induced transparency, that is EIT, which is uses light fields, sometimes modulated, to drive the atoms into a steady state, which is the coherent superposition of the atomic eigenstate. So, in common approaches, signature of the coherent superposition is an altering of the transparencies of the atoms, giving a simple yet sensitive mean of the monitoring the formation of the atomic superposition. So, that is commercially available chip scale atomic clock is the example of utilizing the CPT as well as the EIT of as a fundamental state preparation or detection mechanism of a compact hot atom microwave clock. Another type of the sensor which based upon the cold atomic clouds. So, the advent of the laser cooling that gives the revolution in the atomic sensing. So, the reduced velocity speed of the cloud atoms enabled sensing with longer interrogation times using spatial confined atoms freely falling along the specific trajectory in the vacuum or trapped. It is very easy to understand that whenever we are having a atomic cloud at a particular distance, and they are freely falling along the specific trajectory in the vacuum, then if it is we just reduce the speed of the cloud atoms and it is enabled just to sense for a longer time. Means we are having a clouds, and then we are just reducing the velocity through the laser system. Then we are call it as a cold atomic cloud, and that will be having the reduced velocity, but the time period will be more to interrogate, and that will just calculate and just sense for a longer time. So, freely falling atoms have enabled the development of atomic gravimeters, that will be, and the gyrometer, and that will used for the atomic cloud measures acceleration by sensing the spatial phase shift of a laser beam along its freely falling trajectory. Another is the trapped atoms, which have been employed to detect and image the magnetic field at a micro scale by replicating normal precision spectroscopy on a trapped Bose-Einstein condensation, or by direct driving of the spin flip transition by microwave current. So, we can also use the thermal radio frequency noise in samples. So, sensing with cloud atoms has found application in solid state physics as well as in the novel application of the lasers. That will be the use for the current transport in the microscopic conductors. The most advanced demonstration of the entanglement enhanced quantum sensing have been implemented in the trapped cold atoms and the vapor cell. Means whenever we talk about the cooling of the atoms and the trapping of the atoms, then we are just demonstrating the entanglement phenomena. That entanglement in the form of the spin squeezing, that has been produced by the optically non-destructive measurement of atomic and atomic interaction. So, it has improved the sensitivity of the magnetometry devices beyond the short noise limit and has increased their bandwidth. And that ion trapped in the vacuum using electric or magnetic field that have been extensively explored as a quantum sensor. So, in the most advanced implementations, the quantized motional, that is the vibrational levels of the trapped ions are employed as a sensing qubits. The ions which are trapped, that will be used for the sensing purposes, and it will be in the form of the qubits that enable highly sensitive detection of the weak electric fields and the forces. These motional levels are strongly coupled to the external electric field through the dipole allowed transitions and are sufficiently well separated that to allow efficient state preparation via the Raman sideband cooling or the high fidelity and readout using the laser spectroscopy. Based upon the theoretical and the experimental analysis, these ion traps sensors are predicted to achieve the sensitivities of approximately 500 nanovolt meter inverse and hertz minus 1 by 2 root of hertz. So, for electric field detection, similarly we are having a force for the force sensing acting on a single ion that can also be detected by using these atomic sensors. So, trapped ion have also been widely employed to investigate the electric field noise in the vicinity of the material surface. So, which is believed to originate them charge fluctuations caused by the absorbates. So, such electric field noise represent a major source of decoherence in the ion trap system and superconducting quantum processors, and constitutes a key limiting factor in the development of ultra sensitive force microscopy. So, independently, the ground state spin sublevels of the ions are magnetic field sensitive, qubits analogous to neutral atom, so it is easily detect the magnetic field at a very low quantity. So, there are the various advantages of these ion traps, like ion traps have also been proposed as a rotational sensor that is used in the matter wave Segnek interferometry. So, their uses in the practical application, however, has proven difficult, but practically all the sensing demonstrations have focused on the single ions, which in terms of the absolute sensitivity cannot compete with the ensemble sensors such as the atomic vapor. So, their small size could compensate for their downside in the application, such as microscopy, which is highly spatial resolution is required. So, however, the operation of the ion traps in the close proximity to surface remains a major challenge. Recently, work on a large ion crystal opens, however, the potential for novel application to precise clock and the spectroscopy. Another is the scalable sensor arrays, that is utilize the microlens generated optical tweezers to create the grids of the neutral atoms, allowing for simultaneous high resolution mapping of the magnetic field. Atomic chip, as we discussed, that on the chip wire create micromagnetic trap that must be of the U size or the Z size that allow for the manipulation and positioning of the atom for the local magnetic field measurement. Another is a super sensitivity neutral atom sensor, which includes the vapor cell and the Rydberg atom sensors, often exceptional sensitive for the DC field. So, reaching the sub-femtotesla level and are effective for mapping weak and localized field. Moreover, these sensors has applications and they are used for the high resolution imaging of the surface magnetic field and studying the spin labeled biomolecules as the specialized non-invasive probes in the quantum technology. So, atomic scale probes, we use these sensors. Recently, advanced have demonstrated using the individual atoms on a scanning tunneling microscope tip to detect the magnetic field at the sub-angstrom scale. So, these are the basic applications of the atomic sensors. Now, what are the platform on which it is worked? So, atomic sensor platforms we will discuss in the next lecture. Thank you very much.